Okay, so hi. Our team is comprised of Cesar Lopez,
Pablo Manuel Garrido Juárez.
Santiago Montoya.
and we're going to present you about our Viscometer that we developed over this past semester. So, next slide, please. So basically, our Viscometer works as a special part of a wider project, right? This Viscometer senses when a bubble arrives from this wider project and starts its process of, well, getting the viscosity inside of the bubble, which you can see here. In here, the viscosimeter makes a motor spin at a current, or at a consistent 30 RPMs. The current that the motor draws is sensed by a circuit that we'll present after. And ESP, along with its program, senses this this current in the circuit through an ADC and passes through a formula that compares the viscosity that we know. This formula was developed knowing the viscosity that was in the bubble, which was previously obtained through a lab session, and we generated a formula that I think will be presented afterwards a little bit. And well, the viscosimeter itself rotates and goes up and down. It rotates to go through different stages of the system, and it goes up and down to enter and exit the bubble, right? So yeah, let's continue.
Well, what are the main objectives of this project? Well, we have to measure from reading for the RPMs of a DC motor to obtain the viscosity of different mixtures of soap with water, 50%, 25%, or fully soap. Conditioning, adjust the circuit and signals from the reading of the soap to be precise and reliable for the SP to read the viscosity. What that means? To adjust the IV circuit, to know all the gains and to measure all the resistance. And finally, we need to create a circuit that can be implemented with a motor and a PID control to achieve a different measurement of viscosity.
Yeah, so we developed our research, and we needed to use key knowledge about physics, more specifically thermofluids, and about signal conditioning. We used the op-amps in order to condition the signal to set a gain and an offset. We used the current voltage converter. We used the shunt method because it's really easy to implement, and we can get truly measures of that. We convert the RPMs to centipoc using several formulas. Basically, it's just linear calibration. And we convert to RPMs in a class. That's not important right now. But the size of the bottles and the spindle was designed assuring that we can know the viscosity also analytically. We tried to have as much error as possible to have, based on viscosity, a larger difference in the voltages.
Now the solution for all of this is doing an AB with a differential. So the main point of this is this part, that is the AB configuration for the pump. This one is one on a shunt of 1 watt. That is important and precise. Now here is connected to common ground, but with the combination with the H reach, it changes the combination. I'm going to explain that further. And the gain is a 2 mega and 10K. Actually, we got a gain after many calibrations of 200 that it was working. Also, the capacitor of 3.3 microfarads, it made the signal more smoother. So, well, actually, this is important because the differential amplifier should have an offset connected of the voltage, so it should be like accurate when we have 30 RPMs in zero. But because we put all the gain here and the offset was pretty little, it didn't affect the measurements, so we just don't put the offset. But actually there should be an offset. And this implemented in the Viscometer. For this we made a PCB that is actually here. I want you to, this is a part of the Viscometer. If you want to see the PCB, here it is. For the PCB, here is, all of this is the IV, where these two are the pumps. R9 is the, R9 is the shunt, and U13 is the capacitor. Making all of this is the same that making it in a protoboard. With the little complications that we had when making the PCB, the same program didn't let us connect the ground, one of the pins of the pins of the ground of the H bridge internally to the shunt that is connected to the IV converter. Why? I don't know. It was one of the restrictions inside the program. So what we did to this is connect the third pin, that is one of the grounds of the TVH, connected via jumper is the orange one to a header. So we can have the closure, so we can control the DC motor and also get the IV, because internally the IV has the output of this differential op-amp that is pin number 6 to the ESP, that is all of this in the middle. So by doing this, we assure that have better calibration and have a better measurement for the viscosity. Due to unknown things, really unknown things, the PCB stopped working at one point. It interfered the viscosity with the PID, with the signal of the ultra sensor in the night, like 1 night ago, 2 nights ago. So we preferred it to put in a prototype. That's why we use the PCB just as an example and to show you the design that was intended to be. It was working, but at the last it didn't work because we think the PID has a problem with the signals with the ultra sensor or the color sensor, and that affected our measurement. So to avoid that, we prefer to do it in a prototype.
But finally, what we get of this project? Well, first, the effectiveness of our readings. It was, we can be sure that it's
Reliable.
Consistent. That it's consistent, the measurements. We tried with 50% and the 25% too, and we can see the decreasing of the centipoise of viscosity. We have a trial and error of the IV, more or less, because we change a lot of gains. Finally, we have the importance of the knowledge. All of what we gained through this semester, the knowledge of doing a PCB, the knowledge of doing an IV converter, of using a shunt resistor. We have an open mind to work. The patience, this is most of the important parts of the learns of this semester, because all the night of 3rd of December, when we stay here, it was all about the patient. Because while Cesar and I worked on the PLC system, they were working on the PCB that didn't work to finally put it again on a protocol, on a prototype. And the perseverance for all what we did to this day.
The thickness of the measurements, like
Repeats.
no. It's like to because this effectiveness I added because I wanted to like make clear that changing the gains, changing the measurements, so we had to change the viscosity readings, how we made it. So we have to be like very effective in reading the different viscosity with the different gain, because it actually affected for the voltage, the change of voltage, it affected. So that's why effectiveness is for one for measurement and one for the overall data, like Pablo explained. Thank you.
Okay, thank you guys.